Welcome to the Periodic Trends video. By the end of this video, you should understand what a periodic trend is. You should be able to explain the trends based on atomic structure for each of the following: atomic radius, ionization energy, metallic character, and electronegativity. And you should understand why elements in the same group have similar properties. The electron configuration of an atom determines many of the atom's properties. Since electron configurations show patterns down and across the periodic table, these corresponding properties will also show patterns. Periodic trends, then, is a term that describes the pattern in these atomic properties. We look at trends going down a group and across a period. Remember, groups go up and down, periods go across. When thinking about periodic trends, it's important to understand what's happening with the electrons in the atom. We can think of this generally, and we'll get more specific as the video goes on. But notice that as we go down a group of the periodic table, we're adding principal energy levels. For hydrogen, we have 1 principal energy level. Lithium has 2, sodium has 3. Going across a period, on the other hand, we're adding electrons to the same principal energy level. Let's look at the second period here. Notice that as we add electrons, they're all being added to that second principal energy level. So we're not increasing the number of principal energy levels as we go across a period in the same way as we are going down a group. Keeping these two things in mind will help us understand what comes next. There are 3 main factors that affect periodic properties. The first is how far the electrons are from the nucleus. Recall the Coulomb's law tells us that as the distance between 2 charged particles increases, the attractive force will decrease. The second is effective nuclear charge, abbreviated ZEFF. This is the positive pull an electron experiences from the nucleus. For an atom with only 1 electron, the effective nuclear charge is actually equal to the charge of the nucleus, which is represented with Z. However, once you start adding additional electrons to the atom, the effective nuclear charge actually becomes slightly less than the nuclear charge itself because the electrons on the outermost energy level become shielded by core electrons. So in other words, here we're looking at an atom of lithium with a nuclear charge of 3, but due to electron shielding, due to the presence of additional electrons, the effective nuclear charge felt by each electron is slightly less than 3. Finally, there's electron shielding. This is the repulsion between electrons in an atom. The more electrons there are, the greater the electron shielding. The electrons actually repel each other a little bit on the inside here, so they kind of give each other a little push. And this shields the outermost electrons out here from the full attractive force of the nucleus. Now let's look at each of the periodic properties we'll be covering. For each one, we'll define the property, then we'll look at its trend, and then we'll think about structural reasons to explain the trend. So the first is atomic radius, which is exactly what it sounds like. It's actually the size of the atom. It's determined by taking half of the value of the distance between 2 bonded atoms of the same element. The definition's a little more complicated because consider the fact that given the electron cloud model of the atom, it's hard to really tell where an atom, quote unquote, ends. Therefore, we bond 2 atoms together and take half the distance between the 2 nuclei. But essentially, the atomic radius is just how big the atom is. In order to determine trends, we can graph the data. This is for the first 100 elements. To orient yourself, the peaks of the mountains represent the trend going down a group, whereas the kind of like slopes of the mountains here represent going across a period. So we can see for atomic radius, as you go down a group, atomic radius actually increases, and as you go across a period, atomic radius decreases. We can see that more easily in this graphic. Notice as we go down a group, the atomic radius is getting bigger, and as we go across a period, the atomic radius is getting smaller. Now let's use atomic structure to explain the trends in atomic radius. Recall that as we go down a group, atomic radius increases. This is due to the fact that our valence electrons, as we go down a group, are increasingly far away from the nucleus because of the additional principal energy levels. Therefore, the attraction between the nucleus and those outermost electrons is weaker because, according to Coulomb's law, the distance is increasing. Also consider the fact that even though the nuclear charge is increasing down a group from +1 to +3 to +11, the increased shielding of those core electrons is actually offsetting that increased nuclear charge. That makes the effective nuclear charge relatively constant as you go down a group. So the electrons are getting further away, but they're not actually experiencing increased attraction from the more and more positive nucleus due to the shielding of the core electrons. As you go across a period, however, the effective nuclear charge is increasing. Let's consider period 2. Lithium's nuclear charge is 3+, beryllium's is 4+, boron's 5+, carbon's 6+, and so on and so forth. Since the number of core electrons is remaining constant, the shielding effect will not increase. Therefore, the effective nuclear charge increases across a period because there's no additional shielding and because the charge of the nucleus is increasing. Therefore, the nucleus is able to pull the electrons closer towards itself. So as you go across the period, the radius will actually shrink. Now let's consider ionization energy. Recall that ionization energy is the energy required to remove an electron from an atom. The trend for ionization energy, once again, looking at the peaks of the mountain, we see that down a group, the ionization energy decreases, and looking at the slopes of the mountain, across a period, the ionization energy increases. You'll notice that the explanations for the ionization energy trend are really similar to the explanations for the atomic radius trend. In fact, they're basically identical. As we go down a group, the electrons, once again, are getting further from the nucleus for all the reasons described before, therefore increasing their radius. And if they're getting further away, then they're less tightly bound and require less energy to be removed. Going across a period, again, the electrons are getting closer to the nucleus because of the increased effective nuclear charge. Therefore, they're more tightly bound and require more energy to be removed. Metallic character is not really a quantifiable property, but it relates really closely to ionization energy, so it's sensible to talk about it here. Metallic character is how much an atom acts like a metal. So how does a metal act? Well, here's the general properties of metals. They're shiny, malleable, they lose electrons easily, and they form positive ions. That part about losing electrons easily is the most important part here. The more metallic something is, the more easily it will lose an electron, and therefore we say it's more reactive, since we define reactivity in terms of how easily an electron is lost. This is obviously related to ionization energy, since a lower ionization energy will result in electrons that are more easily lost, which results in a more reactive atom, which results in more metallic character. So in summary, metallic character decreases across a period because electrons are harder to remove because they have increasing ionization energy. And that it increases down a group because electrons are easier to remove. The ionization energy is decreasing. Our final property is electronegativity, or how well an atom attracts bonded electrons to itself. Notice that this is only relevant for atoms that are bonded because we're talking about bonded electrons here. Electronegativity is measured using the Pauling electronegativity scale, where 4 is the highest value. Fluorine is the most electronegative. You'll notice that a few of these noble gases don't have values for electronegativity. Consider the fact that noble gases typically don't bond, so you can't really talk about how well they attract bonded electrons to themselves since they don't exist in bonds. You'll see that the trend here is that electronegativity decreases down a group and increases across a period. Once again, the explanations are the same as they've been all along. As we go down a group, the electrons are farther from the nucleus and experience weaker Coulombic attractions. Therefore, the electrons are less strongly attracted. As we go across a period, the effective nuclear charge is increasing, therefore the electrons are more strongly attracted to the nucleus. A final thing that's important to remember when we're thinking about periodic properties is the properties of groups. Remember, groups go up and down on the periodic table, so there's a group, there's a group, there's a group, there's a group, and so on. Recall that an element's properties are determined by its electron configuration. Also recall that elements in the same group of the periodic table will have the same valence electron configuration. Therefore, we can conclude that elements in the same group will have similar properties. That brings us to the end of this video. Let's review our goals. First, we looked at what a periodic trend is, or a periodic property is. Then we explained the trends for each of the following properties in terms of atomic structure: atomic radius, ionization energy, metallic character, and electronegativity. You should be able to define each of these and explain not just what their trends are across a period and down a group, but also provide structural reasons for those trends. And finally, we recalled that elements in the same group will have similar properties.